So in this video, we're going to go through review 2 for the transformations test. So for number 1, they've given us two triangles that we're looking at here. And they're graphed, and there should be some series of transformations that maps ABC onto EDF. For these multiple choice questions, the strategy is just to go through each choice and see which one maps one figure onto the other. The good news for us is, if I start with number 1, if I start by just reflecting over the x-axis, and again I'm just counting the boxes here to see where these points would land. I'm labeling them just so 1, 2, 3, 4, 1. I know where each individual point lands. So I've reflected over the x-axis, and if I reflect over the y-axis again, I'm noticing that C prime is going to map to F, A prime is going to map to D, and B prime is going to map to E. So that would map my two figures onto one another, and that would also show that they're congruent. Number 3. In the accompanying diagram, AB is parallel to CD, and transversal EF intersects lines AB and CD at G and H, respectively. If CHG is 3x, and the measure of angle AGE is 2x plus 25, what's the measure of angle AGE? Well, remember the image here, right? These are two corresponding angles in parallel lines. Remember that corresponding angles are such that if I translate one of them up or down the transversal, it should map directly onto the other one. So that's a good way to prove that those two angles are congruent. So I'm going to set 3x equal to 2x plus 25. I'm going to subtract 2x on both sides. 3 minus 2 is just 1x. So I find that x is equal to 25, but they want me to substitute back in to figure out AGE. So 2 times 25 plus 25. 2 times 25 is 50, plus another 25 is 75. So the measure of angle AGE in this case is just 75 degrees. Number 4. In the diagram below, triangle ABC and triangle PQR are graphed. Describe a sequence of rigid motions that would map triangle ABC onto PQR. Right, so this is always a little bit easier to do on a coordinate plane, right? Looks like I'm going to have to translate down and then maybe a reflection over the y-axis. So I'm going to count my boxes from C to R just to see how far down I'd have to go. 1, 2, 3, 4, 5, 6. So the first thing I'm going to do is I'm going to translate 6 units down. Now, the helpful thing to do here would be to take all of your points and move them 6 units down, just so that it's a little bit easier to see what your last transformation should be to take you to your final triangle, right? Because if I sketch that pink triangle in, it's a little bit more obvious that if I reflected over the y-axis, these triangles would map exactly onto themselves. So I'm going to say my last transformation here is just to reflect over the y-axis. Usually you won't need more than 2 or 3 to get one triangle onto another. Now this is a little bit easier than on the Euclidean realm because we're able to count boxes and we're able to reference axes, but keep in mind that if you don't have those, you want to be translating one triangle so that they touch, and then a reflection or rotation. Number 5. How many lines of symmetry does a regular hexagon have? Well, remember a hexagon is just a 6-sided figure. And if we're thinking about lines of reflection, or lines of symmetry that I could reflect over to get the same picture, there are going to be 6 such lines. So what you could do is you could sketch out a picture, and I'm going to do this to the best of my ability, of a regular 6-sided hexagon. Regular just means that all the sides and all the angles are the same. And it looks like if I draw a segment going right down the middle there, bisecting both the top and bottom sides, that'd be a pretty good line of reflection. But there are 3 pairs that I could do that with. I could do that over here. I could do that over here as well. And if I fold over any of those lines, the hexagon would map exactly onto itself. But those aren't the only 3 lines of reflections. I could also connect one of the vertexes to the vertex on the other side, like that, or like that, or right across the middle, like that. So if you count up your lines, there's actually 6 different lines there that would show that there are 6 different lines of symmetry for a 6-sided regular hexagon. And that's going to happen every time. So if I'm talking about a pentagon, I would think to myself that, okay, there are 5 sides, so there should be 5 lines of symmetry. That should be true for any regular polygon. Number 6. In triangle PDQ, PD is congruent to DQ. I'm just marking those with those tick marks. And DT is perpendicular to PQ. And remember that perpendicular lines form congruent right angles. If the measure of angle P is 65 degrees, find the measure of angle TDQ. So that little piece up there. There's a couple things you need to notice here. If I've got 2 congruent sides for this big triangle PDQ here, that means that I'm working with an isosceles triangle. And I know some things about isosceles triangles. They've got 2 congruent sides, and they've got 2 congruent base angles as well. Now they already gave me one of the base angles down here, so I can assume that Q is my other base angle of 65 degrees. And because DT is perpendicular to PQ, I know that angle DTQ should be 90 degrees. So if I'm just looking at this right side triangle right here, I know that all the angles in a triangle should sum to 180 degrees. I already have 2 of them, 90 and 65. When I add those, I get 155. And to figure out my missing piece, I'm just going to subtract that from 180. So when I subtract 155 from 180, I find that my missing angle measure is just 25 degrees. As shown in the set of axes below, triangle GHS has those vertices. Graph and state the coordinates of G double prime, H double prime, S double prime, the image of triangle GHS after a rotation of 180 degrees about the origin, followed by a reflection over the x-axis. So the followed by is going to be the second transformation here. The first thing we're going to do is rotate. Now what you could do is you could turn your paper 180 degrees and plot the same triangle. So if you're trying to visualize this, it should be somewhere over there in that quadrant. But we also have a rule for 180 degrees, right? That's going to take some point x comma y, and it's going to negate both the coordinates. So if you did remember that rule, that's probably the easiest way to attack this one. Just by negating your x and y values and plotting those points. So I'm going to take a second to plot those points. Okay, so I plotted my rotation of 180 degrees, and the next thing I need to do is reflect over the x-axis. So in order to do that, I'm just going to count the boxes. So it looks like G double prime would be right there, H double prime, and make sure you're labeling these with double primes, 1, 2, 3, 4, so that you're showing that you have the correct image, because they tell me that the final triangle should be G double prime, H double prime, S double prime. So this is what it would look like if I rotated 180 degrees and then reflected it over the x-axis. So notice that you could have gotten here in one step, that both of these transformations together are the same thing as if I reflected over the y-axis. So just something to keep in mind when you're thinking about a sequence of transformations or just a single transformation that could map my original triangle onto the final image.